to be able to see for himself all his dreams come true. The dreams he worked so hard for. His son, a famous man, married to a beautiful and wealthy woman.
All right. Now tell me why.
If you love listening to this show, please consider giving a rating and a review on Amazon Alexa or wherever you listen. We want to continue bringing you this amazing content, and part of our ability to do that means that we need a big audience. Now, it may not seem like much, but rating and reviewing the show will help more people find us, just like how you found this show. Simply on any podcast platform, search for a show, scroll down to the bottom, and push 5 stars. It's that easy. Thanks for supporting the show. Today, I'm joined by Mark Cann, who is the CEO and Co-CTO of CryomatiKs, a company that produces clean energy from air. Welcome to the show today.
Thank you very much, Scott.
All right, so Mark, your background is in mechanical engineering, system, as well as automotive technology. Can you give us a little bit more elaboration on your background?
Sure. So my background is actually based entirely on hands-on experience as opposed to, say, the degree pathway that a lot of people come into mechanical engineering nowadays. I've been heavily involved in automotive basically my entire life. Since before I could even walk, I was out in the garage. I had automotive businesses where I've disassembled thousands upon thousands of vehicles. And then that actually led to doing product development work for companies who were trying to develop products and were very good at manufacturing products, but not so good at the integration into vehicles and actually how to bring those products to the market. And the energy side actually came about as the goal to be a component supplier. And then going through the process of doing the development work, it's very difficult just to supply a component nowadays. You have to have a fully integrated solution for people. And so it wasn't necessarily our goal to start off in the zero emission platform, but that's definitely where we ended up.
Great. Well, thank you for that introduction. I know when I was growing up, one of my brothers was really into cars, and thank goodness that he was quite handy because I ruined my RX-7 by not putting enough oil. So the engine block basically had to be taken out completely. So I think there's a lot of value in terms of hands-on experience that cannot be gained through just credentials and traditional education. So what is CryomatiKs?
Sure. So CryomatiKs is the core of CryomatiKs is actually product development. So we specialize in creating thermomechanical solutions that happen to zero emissions. And the other side of it is that we implement those solutions through a specific process that's based heavily on services so that we can generate recurring revenue, which feeds back into our product development service. So there's essentially 2 sides to how we operate, which is product development, which is the core, is where the IP comes from. That's how you actually make the thing that makes the thing that people need. The other side of it is your go-to-market, and that's heavily based on services. That's through partnerships, and we can kind of get into some specifics on that if you like. But that essentially becomes our feedback loop on how we continue to develop new products.
So just to be clear for everyone that's listening, again, the problem that you're solving is you're trying to create renewable energy, and specifically, you're trying to capture moisture in the air into water, and that water is then turned into green hydrogen and using electrolysis. Is that right? Or is this
no, so we're not doing anything with hydrogen. So let me back up just a hair. So the world actually runs on energy, doesn't run on electricity. And we have many, many different ways to create electricity, hydro, wind, solar, on and on and on. But you have to have something to go along with it. So a lot of that is going through the grid. So the grid delivers electricity, but you also need energy. Specifically for transportation has to have energy. Your industrial processes, again, all runs on energy as opposed to just electricity by itself. So you have to have a medium. You have to have a way to go from your potential energy, whether it's wind and solar, hydro, whatever it may be, into how it's actually being used. Now, nowadays, the common term is just energy storage. But for the most part, for decades and decades, natural gas played that role, coal played that role, which is that whenever you needed to do something, you converted it as you needed to do it. So what we do is we take the air that all of us are breathing, and when that air is chilled down into a liquid, that's a type of way to store energy. Now, the actual process itself has been around for 120 years. So liquefying air is a proven process that's been around for over a century. What's different about what we do is the way that we take that liquid air and we turn it back into energy or back into work. That's what's different about today than, say, 120 years ago.
So I want to break this down a little bit for everyone. So let's start first with the capturing of the air. That process or technology, is that a passive process that essentially takes the air and then turns it into liquid air? And if when I say liquid oxygen, isn't there energy that's needed to apply to bring it down to a certain chill factor?
Correct. So the same way that you chill water, it turns into ice. So you consume energy in that process, right? When you cool the water down, it takes energy to do that. It's the same way. So when you chill air down into a liquid, you are consuming energy in the process. What's different about liquid air is that because its temperature is below the ambient, you can recuperate most of that energy. Not all of it, but you can recuperate most of it. And so that's what allows the liquid air to function as energy storage, is because you can actually bring back most of that energy that you put into it.
Mm-hmm. So it's almost like it's hovering kind of just at that equilibrium in a way that it really doesn't take a lot to change states. That's really what you're saying, correct?
Yeah, you are taking advantage of the change in phase. So once you go from the gas to the liquid, it allows you to optimize the way you turn it back into energy.
Understood. So once it's in liquid form, then it's stored. And how is it stored?
So it's extremely cold. So it is stored in insulated tanks. There is a little bit of a loss factor to that, which is actually not too far off from where, say, batteries would be. It's about 1% daily, depending on how you're storing it. But there is a loss associated with the temperature difference of it because it is a very cold liquid. Once it is stored, though, because it is a liquid, it can be easily transferred. It can be stored in extremely large quantities at very low cost, which is what's being done today. There's actually a large-scale system that's being built in the UK right now. It's storing 250 megawatt hours of electricity, which is quite a bit. So once you have it in liquid state, that's what opens up all these different options and possibilities.
All right, so I want to go back. The liquid state that's chilled, what is it in either Fahrenheit or Celsius?
It's roughly 300 degrees below zero.
Okay, so it takes quite a bit of energy to keep it there, correct?
Yeah, like I said, it's roughly about a 1% daily. So if you have an insulated container, you're going to have roughly 1% of the total volume of that is going to want to naturally evaporate on its own on a 24-hour basis. So the larger the container, the more time you have. The smaller the container, the less time you have. Surface area either works for you or against you, depending on what it is. But yeah, there is losses associated with storing it, correct?
Okay. Now, typically, hydrogen is used for storing energy. Again, it's kind of neutral until you actually, put the energy into it. But that tends to be fairly, easy to store and then transport. Why oxygen? Why store it in oxygen versus hydrogen?
Well, we don't do pure oxygen by itself because pure oxygen is an oxidizer, which you don't really want to have oxidizers by themselves. So we actually do the air itself. And this is already being done every day, by the way. So any piece of food that you've had is directly or indirectly connected to liquid air. So the air is being chilled every single day. Most of that air is then being split into nitrogen, separate from hydrogen. That nitrogen goes into fertilizer. That's how we grow so much food. At the same time, when you open a bag of chips and those chips are nice and fresh, the air inside that bag was not air. It actually was nitrogen. And so again, that nitrogen comes from the liquid air. And so our entire food cycle, the way the whole world grows food, is based entirely on liquid air. It just happens behind the scenes, so people aren't really aware of it. So it's already very large industrial process, $60 billion a year. Is the industrial gas industry. It's growing rapidly. It's only been maybe in the last 10 years that the energy industry has started to open up to using liquid air as a form of energy storage. And there's actually a lot of large scale systems that are going to be coming online in the next couple of years here. So it is kind of moved out of its traditional role of just providing feedstock to help grow food. And so now it's transitioning over into energy.
Yeah, so interesting. So basically you're not using pure oxygen, you're using really the air and the components in the air, hydrogen included, and potentially even particles and contaminants that's there as well, right?
Yeah, so most of the contaminants are actually filtered out. So because of the cold temperature, all the contaminants, any moisture is actually filtered out as it's being liquefied. Liquid air is also an additional way to do carbon capture. So it hasn't really caught on as a standalone method, but you can just do it as an add-on. So if you're already doing liquid air, you basically already have carbon capture built in because you are filtering the air that gets liquefied. So right now, today, the carbon's being separated, it gets released back into the atmosphere. Once the economics kind of work out, then you'll have carbon capture built in as well.
So once it's in that store state and it's ready for use, tell me about how that gets converted into energy form.
Sure. So here's the easiest way to look at it. If you were to look at, let's take a wind turbine. Okay, so a wind turbine is able to grab the potential energy that's being carried by the wind and convert it into something more useful, such as electricity. And for economic reasons, wind turbines are usually very, very large to cover the upfront cost. And because they're very large, they also rotate very slowly. It's just the nature of that design. If you were to take a wind turbine and you were to shrink it down so that it was small enough that it fits into the palm of your hand, in order for that design to generate power, instead of rotating very slow, it would have to rotate quickly. And that's what we do. We take essentially a wind turbine that is small enough to fit in the palm of your hand, and it rotates anywhere between 20 to 50,000 RPMs, depending on the power level. And the liquid air is used to provide our wind stream to that turbine.
So if I'm understanding correctly, so as it goes from liquid state to air state, it's actually generating a movement, and that movement in the form of essentially airflow is churning these tiny little turbines.
Yeah, so you optimize the change in state from liquid back into a gas. That's converted into a high velocity stream of air, and that stream of air is then turning your turbine.
And when you say high stream of air, how fast are we talking about, whether it's miles per hour or something else?
Again, we usually do it, we look at it more in RPMs. It's kind of the easier way to look at it as opposed to the actual speed of the air. So we look at it as RPM and flow rate. Okay. It's very similar to, say, I don't like to make the analogy to jet turbines because we're kind of in a completely different area. But in terms of the mechanicals of it, it's very similar to the flow rate and the rotation of a micro turbine that would run off, say, jet fuel or kerosene or something like that. But we have no combustion on ours.
Mm-hmm, mm-hmm. So in this process of converting it to air or wind, what kind of energy use is being applied, or none at all?
So there's two different things. There's the accessories that are involved. So we do have a high pressure pump that pressurizes liquid air before it goes into the turbine. And we also have some of the ancillary controls the electronics and things like that. Everything that goes into it is either thermal that's captured from the system or thermal that's captured from the ambient conditions. So like I mentioned before, it's very cold relative to the surrounding air. So we're actually grabbing the thermals from the surrounding air, and that becomes our input.
Mm-hmm. Yeah. So let's switch gears to talk a little bit about from a kind of a way to compare. So this approach that you're talking about, how does it compare in terms of levelized cost relative to traditional, let's say, wind power, solar PV, and of course, turning water into hydrogen, LH2?
So we're not trying to go down the level of grid scale power. There's already other companies that are pursuing doing grid scale power. We're actually focusing more on what we consider to be the high value use cases, which is emergency power, there's transportation. It's any of the use cases that have extremely specific requirements in terms of the upfront costs, the operating costs, and things like that. So that's why, for example, our first go-to-market is a delivery vehicle. Delivery vehicles operate entirely on cost per mile. It's what's their upfront cost, what's their cost per mile. At the same time, those companies are being forced to adjust to having zero emission solutions because they're not going to be able to operate their diesel delivery trucks inside the city limits pretty soon. So in terms of, we don't compete directly with, say, battery powered vehicles. We don't compete directly with fuel cell powered vehicles. We kind of fit a white space in between, which is that you can do lower upfront costs than a fuel cell, but the trade-off is you have less range. You can do more range than a battery electric, but you also can have the equivalent of quick refueling. So we're a bit of a white space between the two existing options that are out there for zero emission transportation.
So, if we're not talking about kind of large scale renewable energy, like solar and some of the other renewable mix, how will this technology make a significant enough of an impact in terms of decarbonization? Well,
there's a few different things. First of all, if you look at the curtailment that's going on, whether it's from wind or for solar, those systems are always looking for a new load. And that's one of the reasons that there's so much interest in electrolyzers right now, is because electrolyzers represent a new load case for those systems. So we're providing a new load for those systems, and that enables what we refer to as wind to wheels, sun to wheels, where you can actually go zero emissions all the way. So straight from your wind turbine or your solar panel directly to moving the vehicle, it's 100% zero emission the entire way. So we're creating a new load for these systems that are coming online. There's only going to be more systems coming online. And just the variable nature of wind and solar is they don't always generate electricity when you need electricity. So there always has to be something to go along with them. That's why wind and solar is being paired with energy storage now. It's no longer by itself. It's always wind and solar plus energy storage. What we're saying is that large scale liquefying of air already exist. So you can take that existing systems that are already out there. They now become your new load for wind and solar. And then we kind of are assisting of turning that back into these high value use cases. So we can take that energy storage and we can make it wind to wheels, sun to wheels.
Understood. What portion of your revenue is more service oriented versus the kind of the licensing or, licensing or something that's more perpetual?
Yeah. So just to be clear, we are still pre-revenue right now. I don't want there to be any misunderstanding. And what we split is the services, which again go through our third-party partners, is what becomes our continuous input for our product development, so that we can kind of avoid the traditional issue of that valley of death of getting new technologies over into the market. But the services and the recurring revenue is very substantial to the overall business model.
Understood. Okay, great. And again, I know you guys are pre-revenue, but what's been kind of the market receptivity or, kind of traction in the sense of either interest or LOIs?
Yeah, so the most common response that we hear from people is, well, this has been tried before, so what are you doing that's different? Again, going back to the 1950s, there was various designs and various solutions that were based on liquid air, whether it's for portable power transportation. And about every 15 to 20 years, there's kind of comes full circle again. And so when you talk to people, they go, yeah, it's great. What are you doing different this time? Because we've heard this before. So I would say the biggest, there's kind of two takeaways, which one is that people might not be familiar with it. And they go, why haven't I heard of it before? Or why am I just now hearing about this? And then the other takeaway is, yeah, it's been tried before. So what's different today? So that's kind of the two biggest responses that you have whenever you're talking to people, because everybody is interested in the benefits, right? I mean, how are you not interested in having the zero emission transportation that's also cost effective and convenient? Of course, everyone's interested in that.
Yeah, makes sense. All right. Well, I want to thank you for joining. I've been joined by Mark Cann, who is the CEO and co-CTO of CryomatiKs.
All right. Thanks, Scott.
If you've enjoyed this episode, take a moment to rate our show on any podcast platform that you listen to. Scroll down to the bottom and push 5 stars. It's that easy. And as always, thanks for listening.